Imagine you open your favorite shopping app. In a matter of seconds, you search for a pair of shoes, process a credit card payment, and track the delivery status of a previous order. Now, think about the machinery making that happen. What would it look like if the app relied on exactly one computer to process your actions, while millions of other people were trying to buy things at the exact same time? The processing line would instantly back up. Every computer chip has a hard limit on how much electricity it can handle and how much heat it can release before it fails. Even the most powerful machine would hit its physical speed limit and freeze under the weight of millions of simultaneous demands. Because of these hardware constraints, relying on a single computer for everything is impossible. To keep our apps running, we have to build systems entirely differently. Think about being assigned a massive research project in school. If you try to do the entire project yourself, it will take weeks of slow, stressful work. But if you gather a team and divide the tasks, one person writes the text, another finds the images, and a third builds the presentation, you finish the project in a fraction of the time. This diagram shows how tech companies apply that exact same logic. Instead of building one giant machine, distributed computing splits the workload across thousands of smaller computers working as a team. This gives immense speed and creates a safety net. If one machine shuts down, the network simply routes the work around it and keeps going. Because these machines divide the labor so seamlessly, you never notice the massive crowd of computers working behind the scenes. You just feel like you are tapping the screen of one incredibly fast device. This raises an interesting mechanical problem. How do thousands of isolated, separate machines coordinate their tasks so perfectly without stepping on each other's toes? Computers don't speak human languages like English or Hindi. To coordinate, they send tiny, separate packets of information back and forth. We call these messages. You can think of this exactly like a group of friends organizing a weekend trip using a smartphone group chat. They ask questions, confirm details, and share files to keep everyone on the same page. Look at this diagram. When you search for shoes, your phone shoots a quick text to the servers saying, "Please send the inventory." This is a request message. The server then fires back its own message with the inventory data. This is the reply message. Every single action you take online, from loading a web page to logging into your bank, begins with this basic two-way conversation between machines. But running a massive network requires a much larger vocabulary. Simple requests and replies aren't enough to keep thousands of computers organized. When you need to move heavy files, the system uses data messages. These are the workhorses that carry actual content, like the continuous stream of a movie. Then we have the Acknowledgement message, or ACK. When you send a WhatsApp text, you get 2 blue ticks to confirm your friend read it. An ACK message does the exact same thing for computers, confirming the data arrived safely. To manage the network, we use control messages. Think of these as the group chat administrator giving orders, telling individual servers when to start, pause a task, or reboot entirely. Finally, the system needs an alert mechanism. If a connection drops or a file goes missing, computers fire off error messages to warn the network that something needs fixing. Using these distinct message types, a massive crowd of isolated computers can organize tasks, fix mistakes, and stay in perfect sync without dissolving into chaos. Let's watch all of these messages work together in high speed during a daily task like clicking play on a YouTube video. This diagram shows the exchange. When you tap play, your phone sends a request message to the cloud. The server locates your video, returning a reply message confirming it exists. To get the video to your screen, the server pushes a heavy stream of data messages down to your phone. Simultaneously, your phone fires back ACK messages, telling the server to keep sending. If your Wi-Fi drops, the data stops flowing. The system recognizes the break and generates an error message, showing a buffering wheel. This dense, multi-step conversation requires thousands of individual messages, yet it all happens in the milliseconds between you tapping the screen and the video starting to play. The modern internet relies entirely on this fast, hidden teamwork. Spreading the workload ensures that no single machine failure can bring down the entire system. There is a trade-off. Building and maintaining this sprawling digital group chat is complex and expensive for the companies that run them. But the next time you stream a show or transfer money online, Take a second to picture the frantic, invisible conversation happening the moment you press a button. The power of our digital world doesn't come from one giant supercomputer. It comes from millions of small machines working together, simply sending messages back and forth.